In this video, I'm going to give a quick demo of the Colab, which is CNN Fundamentals tutorial. In the first cell, we import all the required libraries like PyTorch and Torch Vision. And the output confirms that, our PyTorch version and shows that we have GPU ready for our training. Next, we write a manual convolution function to really understand how a kernel slide across an image. The output clearly shows our custom 3x3 kernel successfully detecting a vertical edge by producing large negative values where the edge occurs. In the next cell runs our manual convolution step by step and creates visualization to make the sliding window concept easier to grasp. The generated plots show exactly how the kernel transforms the input image into output feature map pixel by pixel. Next, we load some classic hand designed kernel used in a traditional image processing like edge detection and sharpening filters. The output displays these classic filters side by side, giving us an intuition for what CNN actually learns to do automatically. Moving to PyTorch, we define a standard nn.conv 2D layer to create how it looks under the hood. The output breaks down the layer's parameters, showing the exact shape of its weight and biases and confirming we have 30 learnables parameters. Next, we experiment with different padding and stride configurations to understand how they affect the spatial dimensions of our feature map. The printed table neatly summarizes how different combinations of kernel size, stride, and padding change the output size from 32 cross 32 down to 16 cross 16. This block explains how multi-channel convolution works, specifically how 3D filters operate on RGB image. The printed text provides a clear mental model. Each color channel gets its own subkernel, and the result are summed together to create a single feature map. Next, we introduce a pooling layer, specifically max pooling and average pooling using a 4x4 matrix. The output demonstrates how pooling down samples the matrix, showing exactly how max pool takes the highest value and average pool takes the mean. Here we apply those pooling operations to a large checkerboard image to visually understand their different effects. The resulting image show how max pooling preserves sharp edges while average pooling creates a blurrier smooth result. Next, we implement the historic LANET 5 architecture from 1998, which pioneered the use of CNN for digit recognition. The output prints the PyTorch model structure showing the alternative conv and average pool layers followed by fully connected layers. Next, we define modern CNN building blocks, combining convolution with the batch normalization and ReLU activation. The output prints the architecture of a modern block, highlighting how these three operations are bundled together in a standard deep learning. This trace function passes a dummy input through both LANET 5 and our modern CNN to track how the feature map sizes changes. The output provides a step-by-step block of the dimensions at very low at every layer, showing how the spatial sizes shrink while the channel depth increases. Next, we set up the data augmentation transforms like random cropping and flipping to artificially expand our training dataset. The output prints out the exact sequence of transformations, including color jitter and normalization that will be applied to our images. To see augmentation in action, we apply these transforms to a simple geometric sample image multiple times. The grid of output images shows how the same original image looks slightly different every time, which prevents the model from overfitting. Next, we download and load the famous CIFAR10 dataset applying the transforms we just defined. The output confirms we have just 50,000 training images across 10 classes and displays a random batch of augmented pictures like birds, cats, and shapes. Next cell simply defines our mainstream looping functions encapsulating the forward pass, loss calculations, and backpropagation. The output confirms that our training and validation functions are successfully loaded into memory. Next, we instantiate our modern CNN and start the actual training process on the CIFAR10 dataset for few epochs. The printed logs show the loss steadily decreasing and the validation accuracy climbing over 80%, indicating the model is learning effectively. Next, we plot the training and validation history to visually inspect our model's learning progress. The output graph shows the loss curves going down and the accuracy curves going up and confirmation successfully training line. Next, we extract the learned weights from the very convolution layer of our trained model and visualize them as images. The output grid reveals that the network has learned to detect fundamentals and visual features like colorful edges and gradients entirely on its own. Next, this hook function captures and displays the intermediate feature maps as a picture of cat passes through the network. The resulting plots show how early layers see simple edges, while deep layers capture more abstract and complex patterns. Next, we define an even more robust production CNN incorporating best practices like dropout and global average pooling. The output prints the comprehensive structure of this production ready model showing its deep channel progression. Next, we define an advanced training function that includes sophisticated techniques like learning rate warm up and cosine annealing. The output just confirms that the advanced training pipeline is ready to be used. Next, we train our production CNN using the advanced training function to see if we can push the accuracy higher. The logs shows the learning rate adjacently dynamically and the model achieving an stronger validation accuracy. Next cell we generate a comprehensive set of plots of evaluates the entire training journey of our production model. The graphs include learning rate schedules alongside the standard loss and accuracy curves giving us completely pictures of the training dynamics. Next, to understand where our model struggle, we calculate a confusion matrix and detailed classification report. The output heat map and text reports show which specific classes like dogs and cats are most frequently confused by the network. In the last cell, we print a handy CNN cheat sheet containing essential formulas and common architecture patterns. The output provides a quick reference guide that you can use when designing your own convolutional neural network. That's it with this video. Thank you.